11b. Electromagnetism. 11.6 Electrical current and magnetism. In the late 1700s and early 1800s, scientists believed that electricity and magnetism were related, but they could not demonstrate how. On ships struck by lightning, sailors sometimes observed that their compasses were affected. Several scientists unsuccessfully attempted to duplicate this effect in the laboratory. In 1820, while he was preparing for a classroom demonstration, the Danish physicist Hans Christian Ørsted noticed that a compass on a nearby table deflected when he sent a current through a wire. He concluded that the current-carrying wire had produced a magnetic field. Ørsted immediately began experimenting with the wire and compass. From his observations, he determined that a compass needle aligns to circular loops around a current-carrying wire. When he published his observations several months later, his report encouraged new experimentation in the scientific community. Figure 11 to 17 shows a current-carrying wire and the direction of the conventional current, which is opposite the flow of electrons. The direction of the magnetic field, the direction in which the magnetic north pole of a compass will point within the field, can be found by the right-hand rule of magnetism. If you grasp a wire so that your right thumb points in the direction of the flow of the conventional current, the magnetic lines of force caused by the current will point in the direction your fingers wrap around the wire. 11.7 Magnetism from electricity. Only a week after Ørsted's discovery was announced in France, the French physicist André Ampère announced a discovery of his own. He found that two allele wires carrying current in the same direction were magnetically attracted. He further found that when he replaced one of the wires with a magnet, the remaining current-carrying wire was deflected away from or attracted to the magnet. Whether it was deflected or attracted depended on the direction of current flow in the wire and the orientation of the magnet. He also discovered that increasing the electrical current increased the strength of the surrounding magnetic field. Later, scientists found that the magnetic field generated by a current-carrying wire is concentrated inside a loop of the wire. This arrangement produces distinct magnetic north and south poles, just as if a bar magnet were inserted through the loop. If the wire is looped multiple times into a coil, the magnetic field strength is multiplied by the number of loops. A coil of wire that acts like a magnet is called a solenoid. See Figure 11-18. In 1823, an English experimenter named William Sturgeon observed that placing a ferromagnetic bar inside a solenoid greatly increased the magnetic field exerted by the solenoid coil. In fact, a solenoid with a pure iron core produced enough magnetic force to lift a piece of iron 20 times as heavy as the iron core. The solenoid's strong magnetic field aligns the ferromagnetic domains in the iron, thus further strengthening the external magnetic field. Electromagnets are critical parts of many appliances you use every day. Some of their important applications are discussed at the end of this chapter. 11.8 Electricity from magnetism. Electrical current produces a magnetic field. Conversely, a magnetic field can produce an electrical current. If a bar magnet is thrust by hand through a coil of wire, Figure 11-20, a current is momentarily produced in the wire, but only while the magnet is moving. When the magnet stops moving, the current stops. Sliding the wire coil along the magnet has the same effect as moving the magnet. Increasing the number of coils or the speed of motion increases the amount of current produced. How does a magnetic field produce an electrical current? A magnetic field affects the motion of electrical charges in a conductor. When the concentration of magnetic field lines near a conductor increases or decreases, a force is exerted on the electrons in the conductor. The highly mobile electrons move through the conductor, creating a current if the conductor is part of an electrical circuit. The faster the magnetic field strength changes, the more electrons move. This effect is called electromagnetic induction. Even when a magnetic field surrounds a conductor, if the field does not change or the conductor does not move through the field, no current is produced. 11.9 Generators and alternating current. Electrical generators are important sources of current. They convert rotational mechanical energy into electrical energy. In a generator, some type of prime mover, such as a steam turbine or engine, rotates a shaft. attached to one or more pairs of strong magnets. The outward-pointing poles alternate north and south in polarity. This assembly is called the rotor. The rotor spins inside a ring formed of tightly wound coils of wire, causing the magnetic field to sweep continuously through the coils. The ring of coils surrounding the rotor is called the stator. The ends of the wire supplying the stator connect to the electrical terminals on the generator. Study Figure 11 to 21 to understand the basic arrangement of a generator. As the north and south magnetic poles alternately pass a coil, a current is induced in the wire if the generator is connected to a complete circuit. When a north pole passes B by a coil, induction produces current in one direction. When a south pole passes, the current flows in the opposite direction to produce an alternating current, AC. Voltage potential also alternates between positive and negative as the rotor passes each coil. This type of generator is the most important source of electricity used today. Figure 11-22 shows a graph of current produced by a rotating AC generator. When the magnetic poles are aligned with the stator coils, the current is maximum. As the magnet poles rotate away from the coils, their field strength decreases and the current drops. When the rotor poles are between the pairs of coils, there are no field lines cutting through the coils, and the current is zero, represented by the horizontal axis. As the rotor continues turning, the magnetic fields increase in the coils, and current starts rising, but in the opposite direction from the first half of the rotation. In the final panel, the current again returns briefly to zero. This cycle repeats as the generator rotor spins within the stator. The AC frequency, or the rate at which the current changes direction, is measured in cycles per second. The SI unit for frequency is the Hertz H2. In the United States and most of the Western Hemisphere, electric companies provide 60 Hertz service to homes, businesses, and industries. So, when you look at a light turned on in your house, it is really flickering 120 times a second because current reverses twice each cycle. The flickering happens so fast that your eye cannot detect it. In most of the rest of the world, the frequency is 50 Hertz. This difference is why you often need special electrical adapters when using portable AC appliances in foreign countries. Some home ape, especially those with motors, are very sensitive to current, so it's important that the electrical frequency be utilities, measure and control electrical frequency causing problems. The concept of frequency applies not only to AC electricity, but to other cyclical measurements as well. These are covered later chapters. Generator prime movers. Most of the electricity we use each day is supplied by electrical generators. The mechanical energy necessary to turn generators usually comes from turbines. A turbine is a machine that converts the energy of a moving fluid into rotational motion. It is shaped like a propeller and can have just a few or many blades or vanes, depending on the fluid that propels it. Steam turbines. Steam turbines are the most common prime mover for commercial electrical generators. They are turned by steam supplied from large boilers called steam generators. After the steam rotates the turbine, it flows out of the turbine and condenses back into water. It is then pumped back to the steam generator to be reheated. There are three main sources of thermal energy that can be used to boil water to steam in a steam generator. Fossil fuels, especially coal, are the most common source of thermal energy. When they burn, chemical energy is converted to thermal energy. Nuclear energy from fissioning uranium is also converted to thermal energy and is far more efficient than fossil fuels. Heat from deep in the earth, or geothermal energy, boils water to steam within the earth. This steam is obtained from deep wells to turn the turbines. Geothermal energy is becoming more important worldwide. It seems inexhaustible. Its high costs are associated with finding and tapping the sources. Water turbines. Hydroelectric plants use the gravitational potential energy of water stored behind dams or in natural waterfalls to provide energy to turn water turbines. Niagara Falls and Hoover Dam are two well-known hydroelectric plants in the United States. The Three Gorges Dam in China the largest hydroelectric dam in the world, has more than 10 times the generation capacity of the Hoover Dam. Wind turbines. Wind power is becoming a profitable method of generating electricity. Wind farms consist of hundreds of wind turbine generators on towers. The generators are propelled by large fan blades that turn when the wind blows. The largest wind farms are capable of generating more than 100 gigawatts of electricity, enough to supply 1 million average households. Gas turbines and diesel generators. The least economical method of producing electricity uses fossil fuels, such as oil or natural gas, in engines that are the prime movers of electrical generators. Electrical utilities may run large gas turbine generators, basically jet engines, to supplement their normal generators during periods of peak electrical loads. Smaller utilities and industrial plants often drive supplemental generators using large diesel engines. At several dollars per gallon for diesel fuel, this is an expensive method of generating electricity. 11.10 Direct current generators. Today, nearly all the electricity we use comes from AC generators, located at commercial power plants. However, there are many limited but important uses of direct current, DC, Chapter 10, that require a source of electricity larger than what can be supplied by the small batteries with which you may be familiar. These uses include emergency power for important or sensitive facilities, like nuclear power plants and nuclear submarines, and backup power for small installa, tie-ins where an AC generator just isn't practical. Wind power is one growing area that uses DC generators almost exclusively. Wind turbine DC generators are necessary because in any wind farm with 2 or more turbines, each turbine turns at different speeds as wind speed varies across the facility. It would be impossible to get hundreds of AC wind turbines synchronized so that they operate at the same frequency. Since all mechanical electrical generators use the same basic principle, the rotational motion coils of wire and magnetic fields, you might expect all generators to produce alternating current. So, how do we obtain direct current from a generator? Most DC generators reverse the locations of the magnets and coils from where they are in an AC generator. The magnets are mounted in the stator, alternating north and south poles. The conductor coils are mounted on the rotor. Since the rotor spins, a means of drawing off the current induced in the rotor coils is provided by a split-ring commutator. See Figure 11-28 top. The end of each wire in a generator from the other segments. Electrical brushes connected to the circuit slip across the face of the commutator as it rotates underneath them. As each coil passes a stationary magnet, a current is induced in the coil. Current flows through the coil in one direction and out the commutator to the circuit. Just as the coils begin passing under the opposite magnetic poles, the gap of the rotating commutator slips under the brushes, briefly cutting off current to the circuit. As the rotor continues to turn, the current in the coil reverses because the coil begins to pass under the opposite magnetic pole. But because the connected commutator segment 15, now under the opposite brush, the current in the circuit flows in the same direction as before. Thus, direct current flows through the circuit. The first widely used generators produced direct current. The great experimenter Michael Faraday discovered the electromagnetic principles that led to the construction of the first DC generator in 1832. Thomas Edison tried to introduce DC generators, a power source, for the electric lamps he invented in 1879. However, these generators were limited in their effectiveness because a high voltage was needed to supply current to customers at any distance from the generator. But a high voltage was dangerous and required thickly insulated wires. Late in the 1800s, Nikola Tesla invented an AC generator that eliminated the restrictions of a DC distribution system. The first commercial AC generating plant and citywide electrical system went into operation in 1893 in Redlands, California. 11.11 Motors. Generators convert mechanical energy to electrical energy using rotating magnets. Motors, on the other hand, are machines that convert electrical energy into rotary mechanical motion. In 1831, Faraday invented a simple DC motor, but his pioneering device was unlike the motors we're familiar with today. That invention would take nearly 50 more years of work by many men on both sides of the Atlantic Ocean. How a motor works differs depending on the kind of current supply. Both AC and DC motors are constructed like their corresponding generators. Discussion of motor theory is beyond the scope of this textbook. However, we can make these generalizations. The speed of AC motors depends on the frequency of the alternating current, and the speed of DC motors depends on the voltage of the direct current supplied to the motor. The structure of the motor, such as how many pairs of magnetic poles are installed, can also affect motor speed and power.